So I want to go over homework 2. So for the first problem, it says, develop a relationship between temperature and activation energy for a situation where the rate doubles for a 10 degree Celsius rise in temperature. So I'm just going to write that down real quick. This is 1A. So we're looking for a relationship between temperature and activation energy, which is E, where the rate doubles for a 10 degrees Celsius rise in temperature. So right away, since the problem is talking about the activation energy, we know that we need to use the Arrhenius equation. And we also have two different temperatures, so we can write that equation down for each temperature. So I'm going to say K1 equals A E minus E over R T1. And then this equation is normally used, so the rate constants, which is this, are highly dependent on temperature. They depend on a few other things. They can depend on a few other things also, but they're normally pretty dependent on temperature. And so this is a way to calculate what your rate constant is if you have, say you've run an experiment and taken data at various temperatures, then you can use this equation to calculate what your activation energy is. And then this is the frequency factor, and it has another name too. It's either, so frequency factor or pre-exponential. And so what the activation energy is normally for a reaction to occur, it requires some sort of energy or activation energy. The only time that might not be the case is if you have free radicals or something like that, to where the reaction just happens spontaneously upon contact. But normally you need some sort of energy to stretch the bonds or distort the bonds, or to overcome the steric or electron forces between the atoms. And another thing is, if you know the reaction rate at one temperature and you know E, then you can figure out what the rate is at another temperature. And I'll actually just do that I'll show you how to do that real quick, just because it's kind of similar to what you're doing in this problem. So going to this, let's say that you know K at, let's say this is T naught. So then let's just say that's K. Let's just say this is K at T naught equals A E minus E over RT. And then let's say that you want to know K T, so A E minus E over RT. So then you can take the ratio of these. So doing that, you end up with, let's see, so you want to divide this one by that one, so K T equals A E minus E over RT divided by K, is that right? Yeah, K T naught equals A E minus E over R T naught. So then that cancels out, and you have and you end up with k t, and you can multiply the k t naught over, so then you have k t naught e minus e over r. Okay, this is actually positive. 1 over t naught minus 1 over t. So then you can see from this, if you know, so say you know the activation, or say you know the rate constant at this temperature, you know what the activation energy is, you should be able to calculate your rate constant at another temperature. So then coming back to this problem, in order to develop this relationship, I'm going to divide that back over. So k t, and I'm going to also change, well, this is okay, kt over k t naught is equal to e and I'm going to also reverse that, so this would be minus e over r 1 over t minus 1 over t naught. So then I want to take the natural log of this. So up here I end up with L natural log of, and I'm just going to start referring to this as, so I'm going to say this is K2, that's K1, and then this would be T2, and that would be T1. So then I have the natural log of K2 over K1 equals minus E over R 1 over T2 minus 1 over T1. And then I can rearrange this, so I want to solve for E over R. So basically I'm just dividing that over. So E over R equals minus natural log K2 over K1 divided by 1 over T2 minus 1 over T1. And then going back to the problem statement, we know that the rate doubles, so we know that K2 over K1 is equal to 2, and when the rate doubles, we know that the temperature rises by 10 degrees, so we know that T2 is equal to T1 plus 10. And I'm just going to erase some stuff real quick. So then we can just plug this stuff into our equation. So we end up with E over R equals minus natural log, and we know that K2 over K1 is 2, so we can put that in. And we know we have 1 over, and then T2 was T1 plus 10 minus 1 over T1. And then we just want to combine these, so we just multiply each side by 1 and add it together, so T1 plus 10, and then this would be T1, so we have E over R equals minus natural log of 2 over T1 minus T1 plus 10 over T1 plus 10 multiplied by T1. So then that cancels out, and we end up with, so E over R equals minus natural log of 2 multiplied by T1 multiplied by T1 plus 10, and this is over 10. So then we want to solve this for T1, so because that's what we're interested in. Well, it's the relationship between temperature and E, so well, technically that's this, but I'm going to solve for T1. So we have T1 multiplied by T1 plus 10 is equal to 10 E over R natural log of 2. For number 2, it says the rate constants of reaction for the isomerization of cyclopropane to propene are given in the following table. And then it gives you a table of temperature and the measured rate constants for the various temperatures, and then it says calculate the activation energy and pre-exponential factor. So what we want to do for this is, let's write this down real quick. So 2. So we're given some data. We're given the temperature and rate constants for various temperatures, and we want to calculate A and E. So there are a couple different ways you can solve this. You can either make a semi-log plot of K and 1 over T, and then you can determine E, the activation energy, from the slope. But the way I always solve these is I just use linear regression. So you need to make a plot, or you can do this in Excel or MATLAB, or if you have a graphing calculator, you can use you can set up a matrix in there with your, or a list with what you're plotting, and then you can calculate. You can use the linear regression function to calculate what A and E are. So I'll just show you real quick how to set that up. So what you're given in the problem is the temperature in degrees C. So you were given 477. Given the rate constant K, and that was 0.0. So what we want to plot is the natural log of K versus 1 over T. So what I usually do with these is I just continue making a table with that information. And also the temperature needs to be in Kelvin. So let's convert the temperature to Kelvin. So that is 750.15. So then we can calculate 1 over a temperature, and remember this is the Kelvin temperature. So what I got for that was 0.00133, 0.00125, 0.00118, 0.00112, and then we need the natural log of the rate constants, so ln K, and so this was minus 8.622, minus 5.915, minus 3.507, minus 1.347. So the reason why this works is if we look at the Arrhenius equation again, we have K equals A E minus E over RT. So once again, if we take the natural log of this, we get ln of K is equal to ln of A minus E over RT. So just rearranging this real quick, we have ln of K is equal to minus E over RT plus ln of A. So if we look at this equation, we can compare that to the equation for a line. So y equals mx plus b. So once you plot the natural log of, well, basically this and the 1 over t, then you can do your linear regression and you'll get a slope and you'll get the y-intercept. And so then you know that the y-intercept is the natural log of a. And then you can solve your slope for your activation energy, or E. So for number 3, it says you have an elementary liquid phase reaction. It says no volume change is taking place in a Cstr with a volume of 10 liters. So let me start writing some of this down. 3. So this is your reaction, A plus 2B to C. It's elementary. Liquid phase. No. Well, I'm just going to, instead of saying no volume change, I'm just going to say V equals V naught. You know that V is equal to 10 liters. And it gives you the, so it gives you the rate in this, so minus R A is equal to K F C A C B squared minus K R C C. And now that we've learned about rate laws for reversible reactions, you should be able to see where this came from. So this rate constant is K forward and then KR for reverse. And since it's elementary, so we have KF CA CB squared minus KR and then CC squared. And then it tells us that KF is equal to 12 liters cubed mole cubed per minute. KR is equal to 1.6 minute minus 1. And then it also tells us what the feed streams are. It tells us the concentration for the feed streams, so we know that CA naught is equal to 1.4 moles per liter. CB naught is equal to 0.8 moles per liter. And then it says that X is 0.7, and it wants to know what the volumetric flow rate is if 70% conversion of the limiting reactant is achieved. So we want to know V naught. And also, just looking at this, we know that B is the limiting reactant, so I'm just going to say this is XB. So the thing that's a little bit different from this problem compared to some of the others is that you're using B as your basis, and a lot of the problems assume that A is your basis. In fact, most of the charts in the book in chapter 3 are using A as the basis, so that's just something to always keep in mind when you're writing down your equations from those charts. So since B is our basis, I'm going to rewrite this equation. So I want to divide everything by 2. So I have 1/2 A plus B to 1/2 C. Alright, so I'm going to approach this problem the same way that I always approach these problems. So if you follow if you go through these problems in kind of ordered steps, it makes it a lot easier. So the first thing I always do is write down the design equation, and I didn't write this down before, but we have a Cstr. So we need to write down the design equation for a Cstr. So that is V is equal to FA naught X over minus RA. And then we can rewrite this as CA naught B naught X over minus RA. So the reason why I like to go in kind of this order is, so we write this down and then right away we see, oh, we need the rate. So then we write down our rate law. And normally at this point you would go ahead and write down the rate law based on what it gives you, but it's already given it to us, so I'll just write that down. Minus RA is equal to K forward CA CB squared minus K reverse CC. And then looking at the rate law, we know that we need the concentrations, so then we can go ahead and write those down. And so that's the stoichiometry part. So let me erase some stuff real quick. So I'm just going to rewrite that real quick. So B 1/2 C. So now we need to do the stoichiometry. So looking at doing the stoichiometry, we can look at the table in chapter 3 for a liquid phase flow reactor for V equals V naught for constant volume. And then we also need to keep in mind that this is for our basis is B, and most of those tables they're using A as their basis. So we can just modify the equations slightly so they're the correct basis. So doing that, we would get CA is equal to CB naught theta A minus A over BX. So you can see what the difference is. Normally, if we were using A as our basis, this would be, well, I'll write them all down. I'll write them down real quick and then go through that. So CB is equal to CB naught 1 minus X, and CC is equal to CB naught theta C plus C over B X. So if we were using A as our basis, which is how the tables are, these would all be CA naught. They'd be multiplied by CA naught, and we would have all of these would be divided by A instead of by B. So, and then this one, so technically this is the same too. You would have B over BX, but B over B is 1, so that's why that's like that. And then why on the table CA is always CA naught theta A, or just 1 minus x, because this is the other thing, these, if you look at what theta is, so theta A is equal to CA naught over CB naught. So this is over whatever the basis is. So in the case of theta B, you would have theta B is equal to CB naught over CB naught, and that's equal to 1. So that's why this is 1, because technically that would be theta B, but we know these are both 1. And then theta C is equal to C naught over C B naught. So all we really need to do now is figure out, we know what CB naught is because it was given somewhere. I think I erased it. So we need to calculate theta A. We already know this is 1. We know that theta C is 0 because there's no C flowing in. So this is 0 divided by, it doesn't matter what CB is because it just equals 0. So we need to find theta A, and then we know what these are, so I'll go through those in a minute. So I'm going to write down I'm just going to write down the concentrations real quick since I erased them. So we know that CA naught is equal to 1.4 moles per liter, and CB naught is equal to 0.8 moles per liter. So then we can calculate theta A. So CA naught 1.4 over CB naught, which is 0.8, and that is equal to 1.75. So that'll go in there. And I'm going to erase these two because it's pretty apparent already that that's 1 and this one's 0. So then for CA, we can say CB naught 0.8 multiplied by 1.75. And I know that technically you could just plug this into here. So if you plugged so rewriting this up here, if you said CB naught, actually I'll write this over here. So CA is equal to CB naught, and then if you just put this equation straight in instead of the number we calculated, this is CA naught over CB naught minus A over B x. So then when you multiply this through, you could just say this is equal to CA naught minus CB naught A over B x. And I'm pointing this out because I think this is how the solution was written, but I find this kind of confusing because the book always puts things in this form, and I always do it like this, and I feel like this is the most straightforward to me. So you can do it how you want, but that's why I'm doing it like this. So we had the 1.75 minus, and then A, since we're using this equation, we have 1/2 divided by B, which is 1, so this is just 1/2 x. And then we can actually calculate this because we know that x is, where was x again? I thought it told us what x was. oh yeah, so xb is equal to 0.7. So plugging in 0.7 for that, we get 1.12 moles per liter. And then doing the same thing for Cb, we have Cb naught, which is 0.8 multiplied by 1 minus x, because that's 1. And then x is 0.7, so this is equal to 0.24 moles per liter. And then doing the same thing for this one, we have Cb naught, which is 0.8 multiplied by, and then 0 plus C, which is 1/2, divided by B, which is 1, x, and then x is 0.7, so if we plug all that in, we get 0.28 moles per liter. So then we should have everything we need to calculate the rate. So I'm going to erase this real quick. So we have the rate is equal to, and we know what Kf and Kf and Kr are equal, so Kf is 12, and normally I should write down all the units, but I'm not going to because I'm going to run out of room. So I already know they work out. So this is equal to 12, and then multiplied by Ca, which was 1.12, multiplied by Cb squared, which was 0.24 squared, minus K reverse, which was 1.6, multiplied by C of C, which was 0.28, and that equals, so minus Ra is equal to 0.326. And then one thing to notice is that it gave us the rate of A, but we actually need the rate of B because that's what we're looking at. And so we know that from stoichiometry, we know that the rate of B is equal to 2 the rate of R. And so from that we get that RB is equal to 0.6. I think that's going off screen. So we get that minus RB is equal to 0.65 moles per liter per minute. So then if we go back to, so sometimes doing all this math, you forget what you're even looking for. So what we're looking for is V naught, and so if we go back to the design equation, I'm going to erase some stuff real quick. So if we go back to the design equation, we have V naught right here, and we should know what everything else is. We know what the volume is. We know what Ca naught is. Actually, so I'm already screwing this up. This is in terms of B. See, this is what I mean. You get really used to just writing things in terms of A, but in this case it's with B as a basis. You need to be really careful with that. So this is RB, RB, CB naught, V naught X. So anyway, we know what the volume is. We know what CB naught is. We know what X is. And we now know what the rate is. So we should be able to just plug everything in and solve for V naught.